So it's a great pleasure to welcome you, Professor Lindsay Greer from University of Cambridge, England, to talk with us today about climate change solutions. I'm thinking is there's going to be, and we're looking at energy transition without rare earth elements. This is super topical here in Sweden, as Sweden is one of the areas where rare earth element mining is, but because of the underlying geology, is a big question. So we're super glad that you've agreed to join us here at Researchers Desk today. So I'm going to hand over to you now. Lindsay, a warm welcome.
Thank you very much indeed, Alasdair. It's a great pleasure to be with you all. And I must say this Researchers Desk initiative seems to be absolutely superb. So congratulations on that. I will attempt to share screen. Is that now up and visible for you?
That's looking absolutely lovely. Now I'll turn my camera off as well, so we get a really nice recording without me in it.
Fine. So I'll touch upon meteorites, magnets, energy transition, and rare earths. And my main obstacle at the moment is getting my slide to move forward. Which, here we go. So I want to draw your attention to this paper. You can be excused if you've missed it so far, since it only came out on 28th of February by Dirk Rabe, who's a Max Planck director in Dusseldorf. And it's just highlighting the importance in relation to sustainability of metals and alloys. And I want to home in on his abstract. So he highlights the issue that production of metal stands for 40% of industrial greenhouse gas emissions, 10% of global energy consumption, many billions of tons of minerals mined, and some of those minerals will be rather low-grade ores for the material you want to extract. So there are just many, many billion tons of byproducts. Now, our particular concern is with the rare earth elements. I should perhaps remark, possibly many of you are already aware that although they are called rare earth elements, they're not particularly rare, at least some of them are not. But there is a problem with supply risk. I will get to that later. And there's certainly a problem that the ores tend to be rather low grade, and so you have to extract an awful lot of stuff to get a small amount of metal. If we looked at a wind turbine, which you have at top left, quite an important thing in the energy transition, especially in windy parts of Europe. It's astonishing, really, how much material goes into making a wind turbine. The topic today is more rare earths than anything else, but I will just remark on the matter of steel, that wind turbines are not a particularly intensive way of gathering energy. So you need a lot of steel for the amount of energy you get, far more, for example, than you would for nuclear power generation. But looking at Dirk Rabe's diagram here, he highlights that there's 2 tons of rare earth elements inside your typical wind turbine in the magnet. Down at the bottom, he's highlighting that the rare earths feature as key components for wind turbines and also, of course, for electric motors in cars. So rare earths are highlighted here. Now, these are known as Sankey diagrams. It's how materials flow through the system from getting them in the first place to where you put them into applications. And on the left-hand column, these materials are ranked by basically whether they are common and easy to get, or whether they're more difficult to obtain and have a higher supply risk. And the red bars are the rare earths, the so-called light rare earth elements and the heavy rare earth elements. And they flow through, there are minor streams into lots of things, but the 2 main pathways you can see going across the diagram are leading into wind turbines and electrical mobility. And in each of those cases, the generators and the motors, is the use of the rare earths is in the permanent magnets, and those are nowadays by far the predominant uses of rare earths. Now, I'm going to take us back to the early 1960s to a quite different story. The research group of Louis Néel in Grenoble worked on a very simple alloy, half and half iron and nickel, and they subjected it to neutron irradiation, and they found that it formed a different ordered structure within the original crystal. This ordering, however, can only occur below 320 Celsius. So on the left at the bottom, we have a crystal structure. It's cubic. You have atoms at the corners of the cubic cell and in the middle of the faces. So we'll call it face-centered cubic. And the two different shadings of the atoms here are just meant to represent iron and nickel. And in the left-hand picture, you're meant to imagine that those iron and nickel are randomly assigned on the sites. When the material orders, the nickel forms a layer in the middle, iron on either side. You have these alternating layers, and that Nail and colleagues were pointing out should have excellent hard magnetic properties. They, of course, at this time in the early 1960s, rare earth magnets had not been discovered. So basically they were not competing with that. They were just trying to get any old permanent magnet. But the point about this ordering only below 320 is that the atoms are very slow moving below that temperature, and that's why the neutron irradiation is needed. If you didn't have the neutron irradiation, it's reckoned that this ordering would take up to about 10,000 years. Then we come forward a decade or so to people looking at meteorites. You're probably aware that these patterns within meteorites were very important historically in indicating that metals are actually crystalline, and so you're getting crystalline orientations here. So not all meteorites are metallic in this way, but some of them are. They are again typically based on iron and nickel, and one of the crystal structures within them is just the one we talked about already, this face-centered cubic. Even more interestingly, the ordering I talked about already is also found in the meteorites. And being in a meteorite, it is given a mineral name based on the original structure T-nite. It's called tetratenite. And it all seemed to fit the pattern that people are familiar with, that the ordering you need to get the properties you want would be extremely slow. And that's okay in meteorites because you've got lots of time. Meteorites cool over millions of years. So from the original Nail work and then the finding of the material in meteorites, in the modern era, a great deal of interest has been attracted to this because in principle, these iron-nickel materials could rival magnets that otherwise would only get the properties through having rare earths present. So this is a review article. It highlights the tetratenite phase. It gives some magnetic properties. I won't go into any details of those. Suffice it to say, they look sufficiently good to be interesting. This is from a different article. They're looking at actual meteorite material and getting magnetic properties that they are claiming would approach those found in the best rare earth-based magnets. The idea is that the phase tetratenite undoubtedly can exist, but can you practically make it? Well, there have been many, many attempts. Neutron irradiation is not attractive. This is one patent application where basically they try very heavy bashing, mechanical deformation of the material to in some way mimic the displacements of the neutron irradiation. They don't actually succeed in getting tetratenite, but they believe they're on the road towards it. Other more exotic things have been tried. This is going from a glassy structure, and they claim that they can get some of the tetratenite in less than 300 hours. So from, they say, hundreds of millions of years in meteorites to 300 hours in the lab. But they're only able to make it in tiny nanometer particles in a small fraction of the material. This is our work. In the classic way of science, we were looking for something totally different. We didn't have magnets in mind at all. We were looking at an iron-nickel-based alloy, but we were interested in the possibility of whether this alloy could avoid crystallization altogether. So you wouldn't have a crystal structure, you would have a glass. Well, we did not succeed. These dendrites, as they're known, are the growth pattern inside the alloy, and they are crystals. and we did not expect to find anything interesting. We expected, based on iron nickel, that the structure in these dendritic forms would be simple face-centered cubic. But on analysis in the X-ray pattern, you look at peaks to determine the phase. For face-centered cubic, you should just have a single peak in this region of the diagram, and we saw a sign of splitting. And that would be characteristic of tetratenite. Life is not simple, however, because you can get this type of splitting by superimposing X-ray peaks characteristic of different crystals in the material. We have a number of different crystal phases present. So it's fair to say that the interpretation of this is not unambiguous, but at least there was a suggestion that we had tetratenite. This is a diffraction pattern. It tells us about the shape of the crystal unit cell, and the tetratenite cell is not cubic, but it's very nearly cubic. It deviates from cubic by only 0.7%. So the point I want to make is that if you looked at this pattern and you did not look very carefully, you might well imagine that it was cubic, and that would not be interesting. But it turns out closer inspection shows that the distances in the patterns are not all the same as each other. It's not, in fact, this pattern is not an exact square. It's very slightly rectangular, and again, it would indicate possible tetratenite. The tetratenite, as I have said already, is formed by an ordering of iron and nickel atoms. You could characterize that by a sort of number that tells you how well ordered the system is. This is a different system, copper gold, but it's a classic example of the same type of ordering. In our samples, the red dots show that we start with something we just cast, simple casting. It's not particularly well ordered. This red dot isn't particularly high, but when we heat the system up, we see it ordering, and then at a critical temperature, it disorders. That's the 320 Celsius that was claimed by Nail. We're seeing it at a different temperature, but this disordering is expected on heating. When you cool, you would expect the system to reorder, but it does not. We don't really have a good explanation for that, but it is at least of interest that when the same experiment, exactly the same experiment, is done on meteorite samples of tetratenite, just the same thing is seen, that you disorder on heating, but you do not reorder on cooling, and it's probably due to local composition changes. The most unambiguous evidence for having the tetratenite phase we're looking for is these so-called forbidden reflections. They shouldn't be there, but we are getting reflections. It's a sign of the phase being not cubic and having some ordering in it. Magnetic properties we have not measured in a way that people who make magnets would be in sympathy with, but you can detect in the electron microscope whether magnetic domains are small and compensating each other in direction, or more like a single domain, which is what you might expect for a permanent magnet material. So again, there's a suggestion that in these middle images for our tetratenite sample, we have something that has desirable magnetic properties. You could ask, since people have been trying to find tetratenite in man-made samples for literally decades and have not succeeded, how is it that we have succeeded? Well, I think the answer could be the presence of phosphorus. When people want to make magnets, you would not think of putting phosphorus in. And people familiar with steels will know that you would actively avoid phosphorus because it makes them horribly brittle. So phosphorus doesn't seem like a naturally desirable thing to add. You probably think of it as an undesirable impurity, but it is found in meteorites. And in meteorites, it was already known that when you add phosphorus to man-made samples trying to mimic meteorites, you greatly speed up the mobility of the atoms. And there have been various computer calculations on this showing you can get many orders of magnitude speeding up of the iron and nickel mobility when you have phosphorus present. That could be one part of the story of how we may have made things move forward a bit. This was our paper. It came out on the 25th of October. It was immediately picked up by the Bloomberg news agency, quoting Joe Biden. I don't suppose Joe Biden knows much about tetratenite or has any particular interest, but for sure he's interested in the rare earths competition with China. Then it just got picked up all across the world very quickly. So it's a big news story. And the reason it's a big news is, of course, not really the magnet bit, it's the rare earth bit. So here's the periodic table of elements. The rare earths are down at the bottom. Neodymium is the most prominent one used in permanent magnets, supplemented by a couple of rare earths that are much more rare and therefore more expensive, dysprosium and terbium. These are sufficiently, although they're only tiny amounts in the magnet, they're sufficiently more expensive than the neodymium that they're having a significant effect on the overall price of the magnets. Supply risk is associated with the fact that at present, most rare earths come from China, and the price, despite what I've just said, is sufficiently low to make it not viable to run other mines across the world, although the deposits do exist. So it's not that rare earths are only found in China, but that is the predominant source at present. And they're certainly highlighted as critical elements of the rare earths. The tetratenite with iron and nickel as the principal components, of course, there's no real supply risk over those. Horrifying is that common metals like aluminium and steel are quite well recycled. Metals on critical lists, some of them are moderately well recycled, like the noble metals, platinum, palladium, but the rare earths are hardly recycled at all. So there's a gross failing. Of course, recycling them is very difficult because you don't have components made out just of rare earths. They would be typically rather small doping amounts in something else. So it'd be rather hard to recycle them, but we really must improve that. And of course, there's concern about the local environmental hazards. China has stopped some mines altogether. Here's the main source of rare earths at present. It must be a horrendous sight. The railroad down at the bottom takes them away for further processing, and that's what it looks like, said to be one of the worst places in the world to work. This just gives you a sense of the current market, or at least back in 2012, the market for permanent magnets. This bright dominant color is iron, neodymium, boron. Greater part of the market, but there are other types of magnet. In relation to our work, we've been thinking of if we could get tetratenite as a workable magnet, where would it fit in the great scheme of things? Well, we would hope that it would have a lower price than iron, neodymium, boron, comparable magnetic properties, but maybe not as good as the best rare earths, but it would have a place in the marketplace in balancing performance and price. Maybe not in one way. We could imagine a cheaper form of it with lower grade properties and a more expensive form with better properties. But would we actually be able to make it? Well, I think it's fair to say that in our original discovery of tetratenite made by simple casting, we were simply just too enthusiastic and optimistic. Because I had basically thought, well, people considered that you could only make tetratenite over millions of years. We've made it in a matter of seconds in a simple casting, job done. The truth is, we must be very far from job done, and the clue is in the meteorites, which have a cloudy zone that has exceptional recording properties for the history, the magnetic history of the meteorite. So that's of great interest. But it turns out that although tetratenite is fairly well distributed in the meteorite, only in this cloudy zone do you actually get the required recording ability, which of course is the ability to have a magnetic moment and keep it in the light of further events, which is of course just the sort of thing you want for your permanent magnet. And in essence, the tetratenite has to be divided into small particles, and they have to be so small that each of them only has one magnetic domain. The graphs on the left are just an example of different properties measured on these two otherwise rather similar meteorites in the cloudy zone, indicating a different magnetic history, forming under a strong magnetic field in one case and essentially no field in the other. So you get different types of cloudy zone. The scale of the droplets within, it would look a little bit like a milky emulsion, except it's happening in a solid, not a liquid. And these droplets, as I'm calling them, may be a few tens of nanometers across. But their size varies with the cooling rate of the meteorite, which varies enormously. This is degrees per million years and a logarithmic scale. And this is nanometer sizes of those droplets of tetratenite. Story is, if you cool too slowly, the tetratenite particles are too big to be single domain. You don't have the right properties. If you cool too fast, you don't have time for that ordering to occur. That's the interpretation in the meteorite world. And in the middle, things are just right. It's quite a broad range. This colored range in the diagram is the range over which you form a cloudy zone that does the magnetic recording job that these people want. But for us trying to make a man-made magnet, how on earth would we get this structure? Well, I don't think we have a route to it. We're thinking about possible processing routes, but my bottom line is to say, I'm quite pessimistic, actually, that we could make a desirable microstructure, as we would call it, to get optimum properties. So my conclusions are that our work, I hope, has contributed to the effort to find a high-performance permanent magnet that would not contain rare earths. There are lots of people across the world working on exactly this same issue. Permanent magnets are important in the energy transition, wind power and electric vehicles. I will just remark that they're not absolutely essential. You could, for example, have electric motors that do not have permanent magnets, but they are less efficient and less ultimately powerful than the motors that have permanent magnets. Meteorite studies undoubtedly show that you can get good magnetic properties without rare earths. But in my assessment, it'll be a very long road from where we are now, preliminary observations, which we interpret as tetratenite, a long road from there to making a practical permanent magnet material. But I expect that there will be a lot of research investment go into this to try to make it happen. That's the end of my slides and my story. Thank you very much.
And thank you, Lindsay. And I was a bit sad at the end. I kind of thought we've got the energy crisis solved. That would have been kind of good. But this is also a wonderful lesson for everyone in how science works. It's not the case of turning to scientists and expecting the silver bullet is naive. We're working very, very hard to try and find solutions, but we're not. And we're making contributions. Lindsay, your work is really fantastic, and I think it's really, really super interesting. And I love your honest way of presenting it, also reflecting on the pluses and the